And it's okay? Okay. You took a chance by saying wonderful lecture. You should wait. It's a great pleasure indeed. I'm sorry to have such a short trip to your country. Too many constraints, too much work at home, and that's life. Great pleasure. It's a very dense visit. I just landed yesterday and flying back tomorrow, and the short trip, lots of lectures. I'm going to collapse in the middle of the lecture. I think I see lots of young people. Okay, everybody's young in the audience, including myself. But I see really young people in the audience. I'm very glad. So it's going to be a non-technical talk, highly non-technical talk. Some of you might even resent the lack of mathematics in the talk. It's also a slightly provocative title. Why are mathematics needed? It's a very deep question, and I will just take a few examples of why they are needed. I started giving a general audience lectures of the type of the one I will be presenting for various reasons. One of the reasons is certain experience that many of us mathematicians, professional mathematicians, have. Is, whenever we are sitting in a train or in a plane, immediately a piece of paper pops up and we start, drawing strange symbols on the piece of paper, and regularly you have people, normal people, sitting next to us, and after a while they get very curious. Well, what are you doing, then you explain, well, in an almost apologetic way. I'm a mathematician. And usually there is so this is slightly frightening for the normal people, and usually you have two kinds of reaction. Most of the time, the normal reaction is, I never understood anything in mathematics. Occasionally, some people say, well, I always loved mathematics. But it's always a love-hate relationship. There is nothing in between. And my usual answer is to both comments. Either I never understood anything, or I always loved mathematics, is neither do I. It's, I think, a good reaction. Because in fact, one should be aware that we professional mathematicians, and that might be comforting for the students here, we know nothing about mathematics. Really nothing. Just a quote by one of my heroes, John von Neumann. John von Neumann, for the young people here, invented so many things. He started in logic, algebraic, even had, really pure algebra research topics at the beginning. He worked in fluid mechanics as a consultant in aerodynamics with the US Air Force. He invented the one possible mathematical way to look at quantum physics. He invented ergodic theory. He invented the game theory. In his free time, he invented the logic behind the modern computers. He was a monster, and in the late 20s he was asked, how much mathematics do you know? And von Neumann always answered immediately any question, because he had always thought about the question beforehand, and his immediate answer was 28%. Okay? So, of course it's a joke, 28%, but that's von Neumann in the late 20s. So I know nothing about mathematics. That's my point. So we should always keep that in mind. We know a few things, and we do our best. So it's normal. That's point number one. Point number two is that also knowing mathematics, we are asking a lot. When we say we know something, we really know it. Which might be a difference with other sciences. Well, anyway, so that's reason number one is indeed the fact that there is a curiosity, and usually, you know, when you have this kind of interactions with, again, normal people, after these initial comments, usually the conversation stops because they are really afraid. But from time to time, they want to know more. They want to say, well, is there anything new to find in mathematics? Which is a very good question. In fact, for us, it seems obvious because we are living in mathematics. But it's a very good question. And then if you want to answer that question, of course, you can explain about the internal logic of mathematics, probably the progress of knowledge in mathematics, but you can also try to give examples. And in fact, there are more and more mathematics everywhere. Okay, so we might not be aware of that, or people may not be aware of that, but this is absolutely incredible. So I will give a few examples in the lecture. However, you're just a tiny, not philosophical, I am not a philosopher, relax. But a general comment is that I tend to believe, and that's not an original thought, that many human activities go all the time towards more virtualization and more abstraction. This is certainly true for, you know, communications, for commerce, money, and even leisure, and so on. This is a trend. It may just reflect the way our brain is functioning. It's an abstract machine for, and it creates concepts. It creates classes. Well, anyway, so this trend towards abstraction, towards virtualization, that of course is obvious. Everybody is talking about digital society and so on, means that there's going to be more and more uses of mathematics. It's going to increase and increase and increase all the time. It's automatic in some sense. Now, there are mathematics everywhere. Fortunately, there are not mathematicians everywhere. But you know, mathematicians can help to use in good ways mathematics. So mathematics indeed everywhere, and this also creates some responsibility. So a slightly provocative comment. I'm always struck that if you look at the history of some sciences, let's take chemistry as an example. Physics is a little bit more mixed, a bit more complicated. Or if you take human and social sciences, or even if you take computer science, it has become impossible to define the art of the discipline. The art has exploded, and it's full of interfaces with all the branches, all the fields, and so on. In mathematics, we are much more used to a core activity in mathematics, but I think this is an old way of looking at mathematics, and that might change. It will also change, I'm pretty sure, in mathematics, and we see the build-up of all those interfaces. At least it's our choice, it's your choice, you young people, to decide what kind of mathematics we want to develop and push. That doesn't mean that theoretical mathematics are not necessary. They are necessary, but the emphasis, the core of the discipline might switch slightly. But anyway, that's enough for blah blah. So what I'm going to talk about is indeed start from applications. You mentioned that I was lucky to get some award, and I got it because of theorems, because of you know, theoretical results which certainly cannot be looked upon as applied mathematics. But at the same time, I've always devoted a great part of my life and a great deal of time dealing with real-world applications. So I'll begin with examples that I know because I worked on them, and I'll try to explain the connections with the theoretical type of math on partial differential equation that I particularly like. Why it was necessary, why you mentioned Boltzmann equation. I will explain why we got interested in France in Boltzmann equation. There was an industrial application that pushed us back on Boltzmann equation. Okay, so I'll start with a bunch of examples. It's going to take some time. It's going to be looking at pictures and without explaining anything, just will see some applications. Fine. Then this is, if you want to summarize, it's going to be about numerical simulations being used for real-world problems. Then I'll say a few words about the mathematical models, and then I'll discuss the why, to give a few examples where it's clear one needs some analysis in order to work well in the context of applications. And I'll mention a few trends and perspectives at the end of the lecture. So it's going to start really slowly by a bunch of examples. So I'm going to show you simulations in a variety of contexts, ranging from space industry to digital pictures. You will see that all those applications have very little in common. In fact, much later I will explain they have something in common at the mathematical level, some kind of equations which have similar form since from very far away, and they are of very different nature from one to the other. Let me tell you that I've really, as I said, spent some time interacting with lots of people from different backgrounds. In fact, I was, just before the lecture, I was thinking I had published papers in physics, in many kinds of physics, but real physics journals, nuclear physics, atomic physics, plasma physics, theoretical physics. I published a book in chemistry with chemists, and I wrote papers in engineering, in computer vision. I wrote paper even in economics, in finance. Just to mention that indeed I've spent some time really looking at lots of applications. Many of those applications share in common certain class of equations, and so the math, in fact, in the end, in some of those applications is just the same. It's the same theoretical basis, but the same theoretical basis can have very different applications. We will see. That's enough blah blah. So let's look at a few examples. So I'm going to use first the computer. Okay, so I hope it starts. Okay, fine. Okay, so
let me just plug in again, because somehow it was.
That's dangerous. What did you do? It was working. No, it's setting up again. Huh? I hope. Yeah.
Okay. No.
That's fine. Don't worry. Yeah, I'm sorry to use an Apple computer. Maybe I shouldn't do that here. Anyway, so. Okay, so. I'm going to take first a few examples taken from a company with whom I do some consulting, which is a space industry. It's called, nowadays it's called EADS, and they are in charge of various types of high-tech stuff. And this one is the famous Ariane 5 rocket, a European rocket. This is, in fact, the simulation of the very early stage of a launch of a rocket. So the first 2 seconds. So the rocket, this is in Kourou. I don't have time to explain everything. Let me just mention that what you see is indeed the rocket, that the big cylinder in the middle, and on both sides you have 2 cylinders which are full of explosives, and they contain more than 200 tons of explosives. So of course you light them up, and here is what happens. This is numerical simulation. I explain why one needs numerical simulation here. So let's start it. Okay, so you see immediately that the two powder kegs create huge jets. Those jets hit the ground, get reflected on the ground, and are going to hit the structure at the bottom, and the shock is going to propagate along the structure and might damage the satellites. Now, there is no way, why does one people make numerical simulations? There is no way you can make experiments. Absolutely too expensive, and even to have captors on that part of the rocket where the action is really taking place, and then the shock propagates. Captors here are immediately burned, destroyed by the violence of the phenomenon. So it's very hard to get some experimental data or even flight data for this initial period of the flight. So this is why, when experience is essentially impossible, are too complicated, that's one of the reasons to use some numerical simulations. I'll come back to what is needed for numerical simulation. Another crucial moment in the flight of the rocket is the separation of stages. Then you will see the upper stage above, which is going to start. The engine of the upper stage is going to start, and once more, the jets which are being created. Oops. Sorry for the music. It was chosen. I think it was AC/DC chosen by the engineers from EADS. So again, jets are being created by the engine, reflect on the lower stage, and can eat the upper stage. And once more, you want to know this happens at an altitude of a few dozens of kilometers. There is no way you can do any kind of experience. Okay, so this is just a movie, like a cartoon. We'll see what's behind. Okay, so that's another example where numerical simulations are needed because it's impossible to do anything else. Okay, so third example, it's about the International Space Station. Let me get rid of that. Okay, so International Space Station, it's about the cargo which is being built by EADS, which is this stuff. It's ATV, automatic transfer vehicle, and it's bringing all kinds of equipment to the International Space Station. So it's not so much about the docking and the mechanics of the docking. What really matters is that, of course, there is an engine. This engine expels all kinds of particles, and those particles may stick on the solar panels. And depending on the quantity of particles that stick to the solar panels, you could damage those solar panels or endanger the lifespan of the International Space Station. So once more, this is taking place. You need to make numerical simulation because there is no way you can make an experiment. Okay, so those are three examples from spatial industry. Here is another example which has a totally different nature. It's a big European collaboration on blood flows. So nothing to do with space, nothing to do with mechanics. It's blood flows. This is the aorta. It's what is called aneurysm, I guess, in English. And let me tell you the story here behind these research efforts that involves the main teams are a team in Switzerland at EPFL around Alfio Quarteroni, and in Milano, and in Paris at INRIA. It has now become a huge European initiative to make numerical simulation for the whole blood circulation, for surgery, and for everything. Why did this project start? It started with a small company in Italy that was building stents, artificial valves, and wanted to export to the United States. So when they gave their product to be analyzed to the FDA, Food and Drugs Administration, that was 20 years ago, the FDA immediately asked several things, not only the usual file about medicine type products, but they requested, 20 years ago, they requested a file about numerical simulations showing that the valve is indeed working as it should, which is borderline, because at that time no one would have been able to really make a proper numerical simulation of those valves, because it's very, very, very difficult. Why is it difficult? I'll show you briefly. You will see the periodic pumping that comes from the heart, and you will see some flow taking place with colors. This is about the pressure, and this is a very tough problem for several reasons. First is that, of course, you have a fluid, that's the blood, and you have walls, and those walls are not rigid, and that's crucial, because we know that if we have rigid arteries, we're in bad shape. Right? So the elasticity is absolutely crucial. In fact, it allows, there should be turbulence in the arteries, but because the walls are elastic, no turbulence happens. If there was turbulence or if the walls are rigid, we would be dead, we'd die. Okay, so that's one of the difficulties. The other difficulty is the fact that the blood is a very complex fluid, full of particles. I mean, all the fluids in our body have nothing to do with air or water in terms of fluid mechanics. They are extremely complex what are called non-Newtonian flows, and the usual models about non-Newtonian flows do not apply. So it took a very, very long time to be able to make proper numerical simulations. I did very little there, and this Alfio Quarterone is in charge of a big group in Europe that is doing such at the highest possible level, which is doing such simulations. So you see, this is another example involving numerical simulation, which has absolutely nothing to do with the space industry. And now I want to show you another type of examples, which is very much related to digital image processing. So this is in fact a small startup company whose scientific director is a former student of mine, and called DXO. It was just sold, in fact, to a big company. And what you're going to see is our mathematical algorithms correcting things which are wrong in the original pictures. So each time I'm going to set up the diaporama, and each time you're going to have before and after. So before, here you have a typical optical distortion. And after, this is totally automatic. There is absolutely no tuning of parameters and everything. This is much more about lighting. This is an intermediate image, manufactured image, which is in in any kind of digital images. So that's a typical phone, typical phone taking pictures. Again, geometry showing here, plus lights, plus contrast, and everything. Original image, again, totally automatic. It's quite striking. I think I love this one. And again, this is possible because you make mathematical models. You do have mathematical algorithms that understand what they are doing. Okay, so a few more pictures, and I'll switch to the other machine. Okay, so one more distortion correction, and I think you get the picture. Yeah, another famous place. This one is interesting. I mean, now the images are much better with the camera phones, but that was really how to make a scanner out of your phone. Okay, so here is a bunch of examples. Let me switch. So I'm going to try to push this back. Now, okay, that works. Let me see if this works as well. I think we should be okay. Let's see. Let's try. It's not over in terms of examples. I'm going to give you another example that I was involved with, which also is something. It's this is a bad picture. You may not see a lot. I'm not sure you see much. This is a research facility for the production of aluminium. It's called an electrolysis tank. And this was a big research project we began about 10 years ago, involving 3 engineers, 3 applied mathematicians, 3 engineers from Péchiné, 3 applied mathematicians, 2 electrochemists, 1 fluid mechanics, 1 guy from computer science, and probably I'm forgetting some other collaborators. And all those guys have to work on this project, have to work together, forgetting their languages, their jargons, their knowledge. I mean, combining their knowledge with a single goal to understand what's going on in this tank. So let me show you some of the aspects. Here what you have is, okay, so you have essentially 2 fluids, which is here melted aluminium. This is the electrolytic bath. What's important is that here you have electrodes, top and bottom. Between those electrodes you have just a few volts of difference, and you have more than 500,000 amperes flowing from one electrode to the other. So extremely violent phenomenon. This is why it's closed, because there are even some gases which are toxic that gets out. It's absolutely impossible to know what's going on inside. The only type of experiment you can make is measure some magnetic field outside, which doesn't tell much, and put some metallic rods. You put them in, take them out, you look how corroded they are, and that's it. While if you want to have the maximal efficiency, you see that there is an interface. You should have the electrodes put as close as possible to the electrode. Okay, right? This is just purely electrochemistry. Very simple to understand, in fact. But the point is that it has to be very close, but if it touches, it breaks down. Okay, so this is very sensitive and huge energy consumption. So you want to understand what's going on, and that could be helpful to design new tanks. So after 5 years, those are intermediate results. Well, numerical simulation, you can visualize through numerical simulations. You can have visualization of various slices inside the bath. So I don't want to comment, and the colors are not too good, but that's it. One more example of numerical simulation. So I'm going to conclude this long list by showing you a bunch of examples that come from image processing. I already mentioned that I've been involved in image processing. I just hope one can see something. Well, this one, no. And this one, not better. Okay, this, let's forget this one. I'm sorry about that, but depends on the light. So, well, maybe this one we'll see. Yeah. Okay. So here is an example. This is a fingerprint, right? And this type of image, that's the original image. This type of fingerprint has been made through ink now. Nowadays, more and more. When enters countries like yours or the States, you put your fingers, and this is now totally electronic, but still the images are far from being perfect. And in order to properly identify a person, you need to check some points which are called characteristic points, and a proper identification for criminal purposes is being made when you get 7 characteristic points. So what are those characteristic points? Typically the center, branching points, terminal points, particular points inside the collections of regions which make a fingerprint. Now, of course, when you have an image like that, you have lots of little blobs and so on. So you have lots of fake characteristic points. They are not characteristic points. You have rupture. You have ways where you have lost the ink. For instance, here, this is not a termination point. This is just because the image is not good. So you need to have a treatment which is entirely based on mathematical equation, which fill the holes, restore the while keeping the true characteristic points. So this is a practical example. Another example which I cannot really give the details, and I'm almost done. This is highly classified, in fact. It's a detection of moving objects in a very noisy background. So this is a sequential image from left to right, top to bottom. And the question is, what can you see which is moving in that series of pictures, in that short movie? So typically, clearly, the human eye automatically detects this little square which is moving slowly from one picture to the other. There is another thing which is moving and which is completely hidden in the noise, which is fluctuating noise, so you cannot just subtract to get rid of the noise. It's just one tiny dot which is moving. Now, the human eye cannot detect it. Processing it, you need to indeed think about some kind of axioms in order to extract those motions. And typically, if you think about shapes in 3D, because it's you have a 2D picture, and then time is like a three-dimensional, a third dimension. You want to design a model which is going to filter out all the motions which are not smooth motion with constant velocity. So this is something that you can translate in geometrical / PDE terms. It's related to the so-called affine curvature that was invented a long time ago, affine geometry, a long time ago. It's an horrendous equation in terms that if you want to make a numerical simulation. And here it is, the equation is down there. So you see du, that's derivatives of u, du over dt, t is a scale. And you have curve of u, acceleration of u. Those are extremely nonlinear expression that involves a bunch of second derivatives. You have space and time. This is very much related to curvature tensors and so on. And the point is that when you write down an equation like that, which is extremely complex and that we got purely from invariance arguments, you know, we want to have certain filtering which is invariant by lots of transformations, fine transformations, then automatically we are led to a certain equation. Now this equation, if we didn't have a theory which is called theory of viscosity solutions, no one would dare to touch it from a numerical purpose. It turned out that we had the theory, and so we knew that this was a well-posed problem, and we had absolutely no fear in making a simulation, and this worked pretty well. So to conclude and show really a bit more the connection, to conclude this series of examples, let me conclude with a very classical test in computer vision, which was proposed by Ulrich some time ago, which is what do you see in that image? So clearly you see that you have this shape like a 10, and you have this shape like a 5, or what you want to call it, huh? Or a snake. Now, engineers, when looking at two shapes, would say, well, okay, let's try some criteria to make the distinction between the two shapes. So a simple criterion is the number of termination points. Well, 2. Number of angles, 1, 2, 3, 4. 1, 2, 3, 4. Same. Okay? So that's why lots of, in computer vision, lots of people had no clue on how to have an algorithm which really makes the distinction. Especially you have difference of orientation. You see that it's not, the shape is not always in the same, there are rotations all over the place. Now, of course, and the reason why it's not that easy, although we clearly see two different shapes, the reason is that to go from that shape to that one, you just have to do one very simple thing, is that you take this little segment and you flip it there, and you go from one shape to the other. So this explains why they are so close in terms of simple tests. Now, of course, if you think that those are curves, clearly those are different curves. And behind the word curve, what in fact identifies a curve is the notion of curvature, how much curved it is. So hence the idea, okay, now let's have a curvature type filtering, and you know, at a certain scale, this is what you get. So this is just the result of the algorithms, and you see the organization. Let's go back. So not only you have 10s and 5s or whatever, those two kinds of shapes, but you clearly see, after where you have made this proper distinction, you clearly see that the 10s are being organized along a square. I'm not sure that you were able to realize that immediately by looking at the picture. It takes some time to detect it. And it's a very simple organization. Very, very simple. So in this type of shape identification, we even produce a software which identifies automatically the logos of facts and so on. I mean, this has had all kinds of very natural industrial applications. So this is just, what did I do? Just a collection of applications in which I was involved. Now comes the time to really discuss what's behind. So first of all, in order to make those numerical simulations, what is needed? Models. And why do we need analysis? Why do we need mathematics? Okay? Now, defining a mathematical model is a very hard job. I was lucky, in order to avoid defining what a model is, I was lucky to find a reference to reading a book by a contemporary Italian writer, a fantastic writer, Italo Calvino. He has a collection called Palomar of short stories, and in that collection of short stories there is one short story which is called Il modello dei modelli, the model of models. And let's look at what he says. Of course, that's in Italian, and that's my translation, and I'm going to translate it in English because I'm not sure it will help. Okay? So, first, build a model, the most perfect, the most logical, the most geometrical as possible. Second, check whether the model corresponds to the case to the practical cases which can be observed through experiments. Third, bring the corrections which are necessary for the model and reality to coincide. That's a good definition of what modeling is. Second, I love this poetic sentence. The construction of a model was thus for him a miracle of an equilibrium miracle between the principles left in the shadows and the experiment, the experience which is inaccessible. And then there is a warning. But if the efficiency of a model is being measured through its invulnerability or its capacity to endure, then the model becomes some kind of fortress whose large walls, big walls, hide what's outside. So always trying to correct models and criticize and discuss models. Okay, so that's the definition of models. It's much better than I could do with my humble words. Italo Calvino did it much better and even warned us. So where do we stand? Numerical simulations are everywhere in order to study and understand reality. I've shown you a few examples. If you take a car, you know, many of us have come to that place in a car. You have mathematical and numerical simulation everywhere in a car. You may know about crash tests, you know, safety tests. They are all numerical now. 90%, just those which are required to be physical are the ones whereby which for the official purposes in factories they are all numerical. You have tires, engines, acoustics, ventilation, air suspension everywhere, electromagnetics for electromagnetic compatibility. There is this famous story about that I like very much. About 10 years ago, a very famous car company in Germany, very well known for its luxury models, and they have series with numbers in hundreds. So I cannot say more. I mean, maybe you will realize. So you know, luxury cars in Germany, you have 3 brands, but with hundreds, there is only one. So anyway, you have 2 test drivers on that are, you know, crossing each other on a ring and just trying the new cars, and one, you know, just honks the other car. In the other car, the airbag deflated. Okay, that was magnetic compatibility. Or deployment of airbags, full of algorithms, numerics, and mathematics. Very hard because it's a flat structure that gets inflated, a very complex surface. Extremely, in fact, an extremely interesting problem. Anyway, so simulations rely upon mathematical models. Now, in those examples I gave, those models involve what is known as partial differential equations and nonlinear ones. PDEs in short. So a PDE, what is it? It's a set of relationships between the partial derivatives of a function. So we know what a function is, we know what a derivative is, and so writing down a PDE is easy. You don't need to know much mathematics in order to write down a partial differential equation. This seems like very simple objects. However, this might be a little misleading. I would like at that stage to remind you of a little bit of the history of those elementary mathematical notions. If you think about differential calculus, probably the first giant in that history was Leibniz, who invented the modern notations of differential calculus. The notions were not clear mathematically, but he invented the notions. Leibniz was a fantastic character. I like to remind the audience always of who Leibniz was. He was a philosopher, a mathematician, he was a diplomat, a card gambler, a womanizer. He was a very interesting guy. Anyway, so Leibniz. Newton, of course, wrote the first ODE, the first dynamical system we know, involving the acceleration, but he had absolutely no idea what the derivatives are. And they fought like madmen about who invented derivatives and so on. Newton had a mystical notion, interpretation of derivatives. So differential calculus slowly emerged in the 19th centuries through many, many mistakes, including quite a few from a French mathematician, namely Cauchy, who first investigated continuity of functions, limits, and then differentiability, and got all the quantifiers wrong. You know, for all epsilon, there exists a eta, and so on. He got it all wrong. But somehow, slowly emerged the right notion. And we could say, okay, that's it. But that's not it. Because when you're interested in PDEs, that's not enough. So let me convince you of that fact. The study of PDE, even historically, has triggered some famous controversies like wave equations, heat equations, and Fourier series, mistakes, shock waves, and Riemann. So let me comment those three examples. Wave equation. Wave equation is a propagation of a wave, let's say in vacuum, and let's take the simplest example on a line. So it's a simple equation which involves an operator which is called D'Alembertian. D'Alembert was the first one to use this equation and to realize that in order to solve it, that's a very classical fact, you can solve it by superimposing two waves, two profiles that are moving one to the right, the other to the left at constant speed. That's a general solution of the wave equation in 1D. That's trivial mathematical exercise. But this is an equation that involves two derivatives. And D'Alembert immediately asked the question, what kind of regularity do we need on the two profiles that we are sending to the right and to the left in order to say it's a solution of the equation? And D'Alembert, although there are two derivatives, says that nowadays the interpretation of what he wrote was you just need one derivative and not two. And Euler disagreed. He immediately said no. One should accept any profile that one can draw with the end. That was the mathematical concept. Now, nowadays, any profile we can draw with the end, the modern interpretation would be a continuous function, right? And in fact, in order to say that this construction provides a solution of the wave equation, you need distribution theory that was invented in the 20th century. And we know nowadays that we don't care. We can take any profile. And it's a solution of the wave equation. Now, Fourier, another interesting character. I don't have time to explain the history and the life of Fourier, a politician, but also a scientist who invented the model of propagation of heat in media, which can be either solid or fluid. So the heat equation, what we call nowadays the heat equation. Now, he had no clue on how to solve it. So he invented Fourier series. Because as we know, exponentials, complex or real, are eigenvectors of derivative operators. D over dx of e to the zx is z times e to the zx. That's an eigenfunction. So that's why sines, which are just imaginary parts, and cosines, real part of complex exponentials, are natural spectral objects associated with partial differential equations, invented Fourier series. But then immediately people were saying, well, but those series, how do they converge? What does that mean? Now, if you think about it, that was the beginning of harmonic analysis. How do Fourier series converge? It was also the beginning of what is known nowadays in scientific computing as spectral methods, using spectral basis to solve, to make numerical simulation. That goes back to Fourier, and everybody is using Fourier series and Fourier transform in all kinds of fields. Mistakes, that's very interesting. Riemann, another giant in the history of mathematics, Riemann was also very much interested in gas dynamics. In gas dynamics, he was interested in particular, he was able to concentrate on one subject which turns out to be absolutely crucial, which is the study of discontinuity. You know that with certain gas dynamics experiments, like shock tube, you know that there are shocks, discontinuities. Now, if you have discontinuities and you have derivatives and it's a nonlinear problem, what does that mean? So Riemann proposed a solution, a discontinuous solution, a purely discontinuous solution, and made a mistake. It's wrong. Because it was difficult. It was later on corrected by Rankine and Hugoniot, but Riemann really asked the very important question, and nowadays in modern scientific computing, people involved in conservation laws and stuff like that use words like Riemann solver, Riemann problem all the time. So those controversies, those difficulties, intrinsic difficulties, explain why in the 20th century we are getting close. We are to our 12 times. Don't worry, we'll get there. And it may necessitate the introduction of other notions in the 20th century. It started with Sobolev, with the Sobolev spaces. Jean Leray, who used those Sobolev spaces to solve Navier-Stokes or proposed a solution for Navier-Stokes equation, a series distribution of Laurent Schwartz, and so on. All this was being absolutely needed because of PDEs and in the end because of application. So for 5 minutes I want to zoom on the example of fluid mechanics and gas dynamics. From a theoretical point of view, I did spend quite a lot of time on those problems in my life, committed several books and so on. So this is a subject I like very much. I think it's a good example. So Euler, always Euler, always go back to Euler. Euler in 1755 wrote the first models for fluids, so-called Euler equation nowadays. This is an incompressible version for, let's say, a fluid like water. Why did he care? This is not so well known. Why did he wrote the Euler equations? Well, he was in fact asked by the King of Prussia to design a fountains, because at that time that was the high-tech of those times, you know, hydraulics. And of course that was Euler, so he's being asked to design a fountain, and he proposed one of the fundamental bricks of the mathematical models for modern fluid dynamics. The first page of his original paper is absolutely fascinating, because Euler writes down, and this was brought to my attention by my friend and colleague Ian Brunier, he writes down, from a physical point of view, this is settled, it's over. There remains a slight analytical difficulty. That was 1755. Nowadays, just to show that analysis can be difficult, nowadays the three-dimensional Euler equations are not completely understood. So the slight analytical difficulty, maybe slight was for Euler, but for us normal people, we are still facing the slight analytical difficulty. We have learned a lot on those equations. There are still major open problems, and it's even more complicated than a famous problem that I will mention later on, and is one of the 7 Clay Prizes. However, from the physical point of view, Euler was maybe a little quick, because in fact D'Alembert paradox applies to the one of the many D'Alembert paradoxes applies to Euler model. So D'Alembert paradox is a theorem you can show. You even got a prize for this theorem, and the theorem says birds cannot fly. Okay, slightly counterintuitive. Birds cannot fly. Well, what does that mean? And let's pause. What D'Alembert is saying is that if you take models of fluids such as this one, with such a model, birds cannot fly. So this is a mathematical, analytical treatment of a model, making a prediction that shows that the model is not okay, and that you have to correct it. So that's one way you can do numerical simulation and test through numerical simulation, but analysis can also help to understand properties which can be, or in sometimes are not, consistent with reality. Okay, so D'Alembert paradox, and the point is that, and this was later on corrected by Navier and Stokes, is that you need to take into account that there is a certain substance in the air. For instance here, birds can fly because the air is not vacuum, right? And the fact, and this is a so-called viscosity term, which is another second order operator. But if you look at the Euler equations, grad is just a derivative. This is a very simple equation to write. If you know the notation of differential calculus, you can write down the formula. And then you don't know how to solve it. Mathematically, completely. We have quite a little bit of understanding. Okay, the story doesn't stop here. It's Boltzmann invented the Boltzmann equation, following some ideas of the great Lord Maxwell on rarefied flows. And nowadays, why did we care in the 80s in Europe? Why did we care so much about the Boltzmann equation? Because there was this big project about the European Space Shuttle, which was the so-called Hermes. And this triggered a lot of research funding, and engineers started, using a lot Boltzmann equation for portions of flights that are taking place at 93 kilometers This is what is taking place at 93 kilometers high. The Mach number, it's probably written somewhere, it must be around 60. Again, at such an altitude, the atmosphere is not dense. That's a rarefied atmosphere. Classical fluid mechanics do not apply because of thermodynamics. I don't have time to explain that. So Boltzmann proposed that, and that's why in France there was a big research initiative to understand better the Boltzmann equation. And we got lucky, and we were able to make some progress on the Boltzmann equation, but because of that context. So this has really triggered again some interest in an old classical problem, on which many people at work, like Hilbert, for instance, and we got lucky. I just mentioned a few names. I'm not writing down the Boltzmann equation. It's too ugly. I love it, but it's really ugly. This is the ongoing history using those fundamental bricks in order to model fluids which are more and more complex. Thanks to numerical simulation, the scope of applications widens. Aerodynamics, we know that. Weather prediction, we know that. Geophysical flows, blood flows, polymer flows. The rheology of polymers is extremely complex. Special effects in cinema. I like to recall that if you take the state of California and you ask where is the biggest computing power, combined computing power in the state of California, you ask yourself whether it's in one of the big California university. No. You ask yourself whether it's in Livermore, big defense center. No. Even Los Alamos is connected to the UC system. No. Hollywood is the answer. Okay. Special effects. Titanic, this monster movie, you know, when after 4 hours of that incredible film, finally the Titanic sinks. It sinks in a numerical sea. Okay, there are things to add because in fact they didn't take the full three-dimensional Navier-Stokes equation, and it shows. Anyway. So let me conclude this modeling part, and then 5 minutes on why is analysis needed and a few perspectives, and we're done. So basically, all those models correspond to an average descriptions of a large number of interacting particles. So that's clearly the case in continuum mechanics, in physics, chemistry, but also it's the case in image processing. I showed you image processing. What are the particles? Those are the pixels. You don't have an interaction given by physical laws. You have to design the interaction in order to get a desired filtering or processing. Okay, so this is like an inverse problem. You need to design the inverse, the interaction, and thus get the desired result. Finance, we know there is something called mathematical finance. That's a very deep question, which is what is the domain of validity of mathematical models in finance? We know that they don't work always, right? But they work sometimes. When? So one of the criteria is clearly, if you look at those models, is that the only hope for mathematical models to work in finance is that they have to be used on so-called liquid products. So liquid in the financial jargon has nothing to do with water. It just means that this is something you can exchange, buy and sell easily. And so now you see the connections. The particles are the traders that buy and sell, and the interaction is the exchange. Right? So if you have a lot of buying and selling, you may hope that there is a mathematical formula. Otherwise, forget it. And many mistakes have been made because people forgot that you add, it's not a sufficient condition, it's certainly a necessary condition. Well, realistic models are always nonlinear, so I have to explain what nonlinearity and linearity means. Well, linearity is that when you add causes, the effects are just being added. When you multiply the causes by 2, by 10, the effect is just being multiplied by 2 and 10. That's a linear situation. Now, in reality, nothing is linear. It's convenient approximation, which has a domain of validity very often, but it's very rare that something is linear. So the Earth is flat. That's what it's a good approximation, local approximation. Then you realize it's a bit more complicated. Now, there is an example showing the difference between linearity and nonlinearity, which is a little bit trivial, but I like it very much. I read it sometimes in an article in a newspaper. It's not my invention, but I like it very much. It's about cooking. So let's make a cake. Okay? So we have a recipe for a cake for 4 people. Now, tonight we're going to be 8. So in terms of ingredients, we just double everything. Okay? That's linearity. Now you prepare the cake and you put it in the oven. Now if you put the cake in the oven the double amount of time, it's not necessary to invite me. That's nonlinearity. Okay, so 2 more notions that explains lots of modern questions, modern scientific questions, and lots of theoretical questions in mathematics, which are extremely hard. Is that more and more we are dealing with complex systems that couple scales. And I should have said, this was on the previous transparency, is that for all those models, the models are being used and are valid at a certain scale. When we're interested in the temperature in that room and we want to make a numerical simulation of what's going on in that room, clearly there is a typical scale, size of the phenomenon, which is of the order of tens of centimeters, at most 1 meter. We are not interested in what's taking place in the atoms which are in the molecules of the air. So this is a different scale. So models are being made to give a description of what's taking place at a certain scale. In image processing it's the same thing, and we have all done that in front of images. We visit a museum and we look at the picture, we look at the painting. We have always done this game of moving a little bit forward to see something, moving backward to see something else. The analysis that the brain makes is scale dependent. So this notion of scale is completely natural from a point of view of images, and the real tough problems in fact couple scales like turbulence and polymer flows and so on. So to summarize, that nonlinear PDEs allow to describe numerous concrete systems at a certain scale by the study of the average behavior of a large number of particles. Okay, and then we know that it may be necessary to revisit classical notions because of those models. Finally, a few words about mathematical analysis and simulation. So what we have seen through this very long introduction to why are mathematics needed is that indeed we have seen applications, we have seen that there are models, equations that very often involve mathematical objects which are PDEs. Now, why do we need analysis? Why do we need mathematicians to help in this picture? First of all, is historically progress between numerical simulation and mathematical analysis go hand in hand. It's not that mathematics go first and then eventually we apply stuff. It goes at the same time, and from time to time the applications go much faster because proving a theorem might be much harder than writing down a code. Progress go hand in hand. Analysis is required for discretization algorithms. I want to give you a very simple example and then draw some consequences. So a very simple example, it's this simple equation, du over dt equal d over dx. The solution is explicit. You take the initial condition, the initial profile. In order to solve that equation, you just push it to the left at constant speed 1. So you just push. It's like the wind blowing from right to left and pushing everything at constant speed. That's it. So pure transport. Now, this is of course a continuous situation. In order to make a numerical simulation, we all know that you need to discretize to go to a discrete set of positions, and that's a mesh. So here this is very simple, and the mesh looks like something like that. So you take equal spacing in space, equal spacing in time. The time steps are delta t. The space steps are delta x. They are supposed to be small enough so that you're close to the continuum regime. At least that's what you hope. And what you look for is indeed not the solution everywhere, but you want, through a numerical simulation, to compute the solution at such discrete points. Okay, this is the usual thing on this very simple example. let me go fast. So now, of course, you have to build up an algorithm for the computer to make the numerical simulation. So you have to replace, you have discrete unknowns, and you have to replace derivatives by difference quotients. After all, the derivative is the limit of a difference quotient. So the du over dt, n stands for the time steps. So n to n plus 1 is just moving in time by delta t. So you move in time by delta t divided by delta t. That's the difference quotient, should be close to du over dt. Now you do the same in space, but you have three possibilities, because in space you can move to the right, to the left, or you can move in a symmetrical fashion to the right and the left, but then you divide by 2 delta x because you have jumped twice. Okay? Three possibilities. They look the same. Okay? For a non-expert, people doing numerical analysis know that there is a huge difference, but they look very much the same. So let's test. Let's ignore mathematics and see what happens. Here's what happens. So let me remind you that the wind is blowing from right to the left and is pushing this curve, which is this flat at 0, a plane with a steep angle, which is being truncated at the level 1. Okay, so this is this step function. Not vertical, it's a very nice piecewise smooth function. And the wind pushes it. Now if you look at the symmetrical difference quotient, moving left and right, the numerical simulation you compute is this garbage. It is garbage because the right solution is just pushing to the left at constant speed. So it has nothing to do with the real solution. If you take a point to the left, you get another garbage. It's not moving. This 0 is not moving. Now if you choose to the right, you have a perfect numerical solution. Okay? So this tiny example that shows that making a slight modification in either going to the left or to the right, or even respecting symmetry and taking, mathematicians we love symmetry, and it might be natural to use symmetry. It's a complete failure. What you have to do is make a discretization upwind, upstream, because the wind is bringing information. So you have to look for the information and discretize in that direction, against the wind, against the current, against the stream. So that's something which is well known since the early 60s, but this is a very tiny example that shows that blind simulations without any kind of mathematical understanding is extremely dangerous. And so analysis can be used in order to make sure that, and the understanding of the PDEs can be used in order to make sure that your numerical simulation do what they should. That's one reason. They can be used in order to predict some properties of the models, like birds cannot fly. And there is a variety of reasons why analysis is being needed, plus the fact that those are fantastic mathematical questions. And I want to mention that for the incompressible three-dimensional Navier-Stokes equation, in 1933, Jean Leray proved the existence of a finite energy solution. In fact, that's a solution in subway spaces. We still don't know if singularities can form in finite time or not. And in fact, this was mentioned in the year 2000 as one of the 7 Clay Prize of so-called most difficult problems in mathematics. I don't buy the most difficult. I mean, those are difficult problems. I think there are much more other difficult problems, but certainly this is a tough one. Just to show this. So, about trends and perspective, it's time to stop. I want just to mention briefly that indeed the analysis of PDEs might look like a zoo from a non-PDE guy, because so many equations, so many different problems, and so on. It reflects reality. We are living in a world where there is more than 150,000 species of butterflies. So this variety of problems, and that's life. So the unity may take some time, and might not just be possible. So that's part of the difficulty, but the problems can be extremely difficult because of the nonlinearity, formation of shocks and so on. This explains some of the difficulties that analysis are encountering. So which means that for practical applications, engineers cannot wait centuries for centuries while mathematicians are trying to solve the problem. So you have to learn how to do with a partial understanding of the problem. That's also very important in the communication. Plus the fact there are lots and lots of new applications that are bringing new mathematical developments all over the place. Recently I've been involved in lots of modeling in what could be called social sciences, among which economics and so on. I even have a startup company doing this kind of thing, big data crunching on social networks like Facebook and so on. So this is another story. This is so-called min-field games theory that we propose that provide lots of new models which raise thousands of questions from a mathematical point of view. Why social sciences? Well, because also we are observing more and more data, and we are observing regularity in those data. If you look at the distribution of wealth in a country like France or Germany and so on, and you look at it in constant euro, you see that a great portion of the distribution of wealth just stayed the same for a period of 30 years. And not only stays the same, but it's completely identified. It's almost a perfect inverse power distribution, and with the same exponent for 30 years, and slightly different from one country to the other. I don't know about Korea, South Korea. It might just be the same. In the States, is the same, and so on. Distribution of size of big cities in a country. In terms of population, you take off, well, in a country like Korea, you should take off Seoul. That's a monster. Take it off. Like Paris, take it off. Now, if you take off a few huge cities, now you look at the distributions of towns, inverse power, perfect laws. It's essentially the same everywhere around the world. If you look at the distributions of retweets, now Twitter for the young crowd. So take off Lady Gaga, which is number 1. Take off Obama, which is number 6, in terms of numbers of retweet per day, and look at the distribution of retweet per, topic, like Lady Gaga, Obama, and perfect inverse power distribution. I strongly believe that there are some mathematical explanations. We are proposing models that explain why you have such inverse powers distribution, but those are regularities which are really asking for some mathematical understanding. So this is just because of social networks and so on, this is building up, and the use of social networks, which is changing our life in ways we have not yet fully understood. So this is something which is emerging. Another thing which is emerging, which is much more the field of my wife. She's also a mathematician, a probabilist, working in interaction between probability and biology. Now, what's happening in biology requires probabilistic models and combinations of analysis and PDEs and probability because of the variety of situations that you have in biological life. This is clearly building up a new source of problems, and historically we know that most of the time we'll need new mathematics to tackle new applications. So this is a really fun time. There are fantastic classical problems in mathematics, in theoretical mathematics, but there are also other kinds of theoretical problems that are building up, being created by applications like those I presented, which are essentially classical applications, and new applications which are developing. So I think it's a very nice time to get into mathematics. Now I'm addressing directly for the young crowd here. You have a big choice of type of problems that you can tackle, either classical ones or non-classical ones. But anyway, I'm sure it's going to be a lot of fun for the next generations to work in mathematics, because this is building up. I strongly believe that not only we have mathematics all over the place, but more and more mathematics are going to be needed in the next decades, in the next century. That's my conviction. You may disagree with that. And mathematics are needed, and I try to convince you that also maybe mathematicians are needed to use well mathematics, because it's very easy to mishandle mathematics and just use it as a tool. But this is a complicated tool, and you better know how to use it. Well, anyway, so good luck for the young people. It's a nice time to get into mathematics, and I'm sure that with luck you will enjoy it as much as I do, and you clearly saw that I do enjoy the type of stuff I'm doing. Thank you very much for your patience.